Rolling.
Yeah.
Action. Okay. All right, so guys, our plan today, 5I.2, we're going to go over together, and we won't spend long doing it, and then we'll move on to 6A, and that's where we're going to dedicate most of our efforts. After recess, when we come back, we've got a couple of exam questions in our notebooks to go over, so we'll address those. So let's start with 5I.2. We're talking about, I know Slats, you were saying this is why you studied specialist maths, because you want to know the right-hand rule, direction of the vector. So if we have vectors v and vectors u, okay, they compose a plane together, and we want to know when we find the vector of v cross u, that's a vector that's perpendicular to both of them. All right. So if we have vector v and vector u, and we're finding v cross u, what we do is we put our fingers on vector v, and then we spin them towards vector u. Okay, so you can't spin your fingers back that way. All right, they're rotating inwards. And which way is our thumb pointing? Into the board. So that means the direction of v cross u is into the board. All right. So from v to u, our thumb is pointing into board. And similarly, if we consider the vector of u to v, we're rotating our fingers from u to v, my thumb is pointing out of the board. Okay, so that's its direction. All right, so just getting you to understand that when we find the vector of v cross u and u cross v, they're opposite in direction, but they'll be equal in magnitude. Okay, now we're going to just go to question 2 from the textbook. The proof we may address, this proof we may address later, but I've started to write that here, so I'll spin this around. So I've got these two vectors, vector A and vector B. Okay, part A says find A dot B and A cross B. Okay, so for part A dot B, we're just doing the x components multiplied together. So we'll have 2 times 1 plus the y components multiplied together, and then plus the z components multiplied together. Add them up, so we'll have 2 plus 0, take 3, we have minus 1. So the dot product of A and B is minus 1. Okay, next we're going to find the cross product, and we're going to use the correct procedure here. So we'll put I, J, K at the top. And Hayley, this will be your first time seeing it, so we'll just we'll go through it slowly. Then we're finding vector A cross B, so that means vector A is the one we write underneath it next. So 2, minus 1, and 3. And then we have vector B is 1, 0, and minus 1. Okay. So we start with I. All right. We're going to cover up the row I and the first column and the first row, and we're left with this 2 by 2 matrix, and we do AD take away BC. So minus 1 times minus 1, it's going to be 1. Take away B times C, 3 times 0, that's going to be 0. So that gives us the I component. Okay, so we have I, then we have take away J. All right, we're going to cover up the J column, sorry, and we're going to do again AD take away BC. So minus 2, take away, and then positive, take away 3. That's our J. And then we have plus K. All right, cover up our K. AD, so 2 times 0 is 0. Take away minus 1. So let's evaluate that. We're going to have I plus 5J plus K. So the vector that's the cross product then is 1, 5, 1. So we've found A dot B and A cross B. Okay, that's our answer to part A. Okay, then we're introducing you, we've got 2 formulas that we're going to use here that have come up in part B and part D, and the proof of those is on the previous page, on page 31, so I'll leave that for you guys to have a look at if you're interested. But proof's not so necessary, we're mainly interested in using it. So we have find cos theta given A dot B is equal to the modulus A, the modulus of B cos theta. So I might just write beneath vectors A and B their modulus first, so we can just evaluate them quickly. So we'll have 2 squared plus 1 squared plus 3 squared, so 4, 5 plus 9 is 14. And for vector B, we'll have root 2. Okay, so let's put it into that formula. We have A dot B is equal to the modulus of A, modulus of B, cos theta. All right, we found the dot product. We saw the dot product is minus 1. We've got the modulus of A is root 14. We've got the modulus of B is root 2. And we're asked to find cos theta. We're not asked to find the angle, we're just asked to find a value for cos theta. And so rearranging this, we can see cos theta is minus 1 on, and we can combine that surd there if you want. We can leave it separate, doesn't matter, root 28. Okay, we'll do part C as well. So this is the Pythagorean identity. So we've got part A here, that's the cross product, that's part A, this is part B, here's part C. I'll have it go up here. So the Pythagorean identity is sine squared theta plus cos squared theta is 1. Now we've got a value for cos theta, so we're just going to evaluate and find the value for sine theta. I'm going to take that and plug it into our Pythagorean identity. So we'll have sine squared theta plus, and the cos value is negative 1 on root 28 squared, and then we're just rearranging that for sine. So positive or negative. Now you might think back to year 11 methods. When we're solving these previously, often we're given a region for which it's constrained to. Here we don't have a region, so it could be the positive value of sine or the negative value. Okay, and then on to part D. So I'm going to erase the working here for the cross product. Oh dear, I just rubbed out what it was though. It was 1, 5, what was it, 1, 5, 1? For A cross B? Yeah, excellent, cool. Okay, so that's what it is. So now let's put it into part D. Find sine theta, so we're confirming a relationship here. Find sine theta given A cross B is equal to modulus of A, modulus of B, sine of theta. And that's a modulus there as well. Okay, so the modulus of A cross B, this component is going to be equal to the square root of 1 squared plus 5 squared plus 1 squared. That's root 25. And we have A is root 14. And we have B is root, sorry, that's 27, isn't it? 5 squared plus 1 plus 1. 5 squared plus 1 squared plus 1 squared. Root 14, and that's root 2. And then we have sine theta. And rearranging for sine theta, we see we get root 27 on root 14, root 2, root 28, which is exactly what we had before as well. All right. So that was question 2 from the textbook. That's a good recap of 5I.2, or a good insight into 5I.2. So that's all we're going to do from 5I.2. Let's move on to 6A then, where we're going to talk about area. So we've finished chapter 5, and we're on to chapter 6. And what we're going to look at, we've got area of triangles and area of parallelograms, and we will just go through question 1 there. Over the page, question 2, you have the volume of a parallelepiped. And though that's beyond the scope of the course, it used to be in the course, this is an old exam question. It may be something we address a bit later, but it's not required for the course anymore. So let's get into area and area of a triangle and parallelogram. So we've got a beautiful proof for the formula there. we'll just get straight into our example. Figure 1 shows A, B, and P in 3-dimensional space. So here we have A, 0, -3, and 1. Here we have B, I might move it a little bit closer. B, and we've got 3, 2, 2. And then we have C, no, P, which is 4, -1, 3. Now, whenever you're doing vectors, all right, it's you have to make sure you get the numbers right, because if you have one number wrong, it just messes up the whole problem, doesn't it? But again, like in a test situation, exam situation, it's about the process, it's not about the right answer. So you still get marks for following the correct process. That's what we're mostly interested in. All right, so we have these points in space. Part A, find A, B. Okay, find vector A, B. The vector from A to B is the coordinates of B, take the coordinates of A. So that's going to be 3 take 0, that'll be 3. 2 take -3, 5. 2 take 1, 1. We've got vector A, B. Okay, part B says find the area of triangle APB. Now the reason it got us to find vector AB is because if we have a triangle composed of, let's just come up with 2 vectors P and Q, okay, that the area of this triangle, here's the formula, half modulus of P cross Q. Okay, so we've found vector AB. Now that means we're not going to find vector PB or anything like that. We're going to find vector AP. We want the vector from that point, from point A. So let's find vector from A to P. So we've got 4 take 0, -1 take -3, that's -1 plus 3, and 3 take away 1, 4, 2, 2 for AP. All right, so then the area of our triangle then, triangle APB, is going to be half the modulus of AB cross AP. All right, just following the formula, we've got vector AB, we've got vector AP, the area is going to be half the modulus of it. Okay, so the first thing we'll do then is find the cross product of AB cross AP. So we can do that manually, you can use your calculator, it's really up to you which process you opt for. I'll go through it manually again. So we've got I, J, and K. We have vector AB, so 3, 5, 1, and vector AP, 4, 2, 2. Okay, ratio. Cover up I, we've got 10, take away 2, we'll have 8. Take away J, cover up J, 4, take away 6. All right, 4 take away 6 will be -2. And then cover up K, we'll have 6, take away 20, we'll have -14. All right, so that gives us 8, +2, and -14. Would it not be 6? 6 take 4, that's +2. Yeah. All right, so that's our, that's the vector of AB cross AP. So that's the resultant vector. Now, just following the formula, we have the modulus of it, and then half times the modulus of it. So that means the triangle, the area is going to be half, and the modulus is the square root of each component squared. 8 squared plus 2 squared plus 14 squared. So that's half square root, and we'll have 64 plus 4 plus, I don't know that, 196. 196. So that's root 264. Nice. Now the other thing is the software I gave you on your calculator is if you're following those processes, so it tells you these values, but it also tells you the length of it. It will split out the length and spit out the length. Okay, so that's the area of triangle APB. So I think all of that's pretty straightforward, but it does get a little bit creative next because it says, now find the coordinates of C on the line AB. So it's like, now this is where we're introducing a bit of problem solving to something that would be a little bit trickier. Find the coordinates of C here. We don't know what they are, such that, find the coordinates of C on line AB such that the area of triangle APC, okay? So that this new triangle we have is twice the area of triangle APB. So it doesn't have an area of a half root 264, it has an area of root 264, okay? So we've got to find the coordinates of C that make this true. So, we're gonna unveil a property of cross product here. All right, so we'll go through it slowly, and then the property will pop up as we're going through it. So, when I wrote this problem, I thought there's sort of two ways of doing it, right? You could find vector AC in terms of x, y, and z, and then do the cross product of AC and AP and make it equal to root 264. The problem with that is that you have three variables, okay? So it's like a complex system of simultaneous equations. So that's not the process I recommend doing, although you can access a solution that way. I reckon the best way to do this is because these points are collinear, all right? Because these points are collinear, what it means is that vector AC is equal to some scalar multiplied by vector AB. So let's use lambda, because we haven't had that pop up yet. And we've got A's and B's and P's and Q's and X's and Y's and Z's. So I think lambda is a good one for us to use. All I'm saying is vector AC is some multiple of vector AB because it lies on the same line. We don't know what the value of lambda is. That's what we're going to find out. Now we've already found vector AB. Okay, so what it means then is vector AC is equal to lambda multiplied by vector AB, 3, 5, 1. All right, which is 3 lambda, 5 lambda, and lambda. Okay. So then what we want is we want the area of triangle. So this is part C, isn't it? We want the area of triangle APC to equal not half of root 264, but twice the area. So if I multiply this by 2, I just have root 264. So that's the constraints that we have. We have the area of this triangle is APC. So what we're going to do then is find lambda and work backwards to find the coordinates of C. All right, so we know the area of a triangle then is going to be, let's write out the formula for it. Sorry, that's not a vector. The area of a triangle is half the modulus of AP cross AC. Because we're doing the modulus of it, it doesn't matter what order we write these in. I'm actually going to just flip that around the other way so we can see the relationship with how we stated it initially. AC cross AP. All right, so here's the best way to think about it. So that means we've got half, and we've got lambda times vector AB cross vector AP. Okay. Now, one of the properties of modulus is that if we have the modulus of AB, it's equal to the modulus of A times the modulus of B, right? And so that lambda, what we're effectively going to do is pull it out the front, okay? But let's demonstrate why that's true when we use the cross product. So if we go up here, let's focus on this step. Okay, let's assume we don't know that length there yet. Let's focus on this step. We've got vector AC here, and we're going to do the cross product of vector AP. So vector AC is this, but we've just got lambdas tacked on there. And vector AP is this one here. Okay, so then let's go through and do the cross product. Now this is where you do need to know the cross product manually because we've got a variable rather than just a number. So we'll cover up I. We're going to have 10 lambda take away 2 lambda. All right, 10 lambda take away 2 lambda, that gives me 8 lambda. All right, so I'm just pointing out that this is a true property. Cover up the j, so we have take away j, and then I have 6 lambda, take away 4 lambda. So 6, take away 4, 2 lambda. And then cover up the k. 6 lambda, take away 20 lambda, minus 14 lambda. So the resultant vector is this one, of which lambda is a common scalar quantity, which we can factorize. Okay, so we could express it like this, 8 minus 2 minus 14, with lambda out the front. And so that's all I'm saying here, that this is equal to this, half the modulus of lambda, the modulus of AB cross AP. Okay, so I've got to clear some space. I'm going to clear out the cross product. We're almost there. So I'm going to clear this too. All right, so we have the area of this triangle is equal to the square root of 264. We also know that half AB cross AP, let's write it like this, lambda half AB cross AP, okay? We know that this component here, we evaluated that before. We evaluated that in part A. And we know that this component is the area of the initial triangle of APB, which is half root 264. The area of this triangle is half root 264. So what we have then is lambda times half of root 264 equals root 264. What's the value of lambda that makes this true? So minus 2, plus or minus 2. Very good. Okay, and all that means, right, in terms of the context of the problem, is that C can be here, or it can be down here, such that triangle ACP has the same area as triangle ACP. It lies on the line. There's 2 possible solutions. Okay, let's just investigate the positive case. So let's, for now, let's just look at the positive case. Lambda is positive 2. Now, what are we doing? Okay, so we've gone through all of that. We've found the value of lambda. We're asked, what are the coordinates of C? What's the coordinates of C such that triangle APC is twice the area of triangle ABC? Well, we know AC equals lambda AB. So we're just following this. We've got lambda equals 2. So now we've found vector AC exactly, right? Lambda is 2, therefore vector AC is 3 times 2 is 6, 5 times 2 is 10, and 1 lot of lambda is 2. So I've just put the lambda into there. We have vector AC. Okay, we're going back to like 5A and 5B. How do we find the coordinates of C? All right, we need vector OC. Vector OC is equal to vector OA plus AC. All right, so A and A are the same, and we're left with the vector from O to C. We're starting at O, finishing at C. A and A are the same, so they're connecting head and tail. And vector OC is the same as the coordinates of C, isn't it? So that means we're left with vector OA is this one, 0, 3, minus 3 and 1, plus, and this one, 6, 10, 2. And we're left with 6, 7, and 3. So the coordinates of C then, 6, 7, 3. All right, so that's quite a long problem. Hopefully you're able to squeeze it on there. But this is the property we're pointing out, right? Maybe I can just list it nice and clearly is that if we have, so two vectors A and B, and we have KA, not dot product, K is a constant. So if we have KA cross B, all right, it's equal to the modulus of KA cross B. Modulus of KA cross B is modulus of K, modulus of A cross B. We can pull it out the front. Don't think of it in terms of like we're factorizing, because cross product is more akin to multiplication than it is to factorization. And so it's like like K times A times B. So we're just pulling it out the front rather than factorizing. Okay, so what I would like you to do then, let's try a little bit of chapter 6a. All right, so I said 5I.2, we addressed that question together. So we're on to questions exercise 6a. And look, that is going to be where we're going to dedicate our efforts today. It's a short exercise, but we will, when we come back from recess, we've got a couple of exam questions from vector proofs to go over together. Vector proof exam question 2 and vector proof exam question 1. Any questions? No. It's good to